Hanging in there? Semester in full gear? Okay, good. So I hope that you are being able to, or that that you're having a good time in the class. Are there any technical or administrative questions at this point? Any questions at all? Okay. So what we're going to do today is continue our discussion about stress and strain, and we're going to link that to intrinsic material properties today and in the next meeting that we have together. Okay. So last time we introduced stress and strain, and today we're going to go through how we characterize the tensile and compressive properties of materials, and we'll talk about the relationships between stress and strain for some of these materials. We'll talk about elastic moduli, and we'll also talk a little bit about yield strength, okay, and how things fail. So last time we introduced stress and strain, and at this point I think it's pretty clear that stress is acting over a cross-sectional area, and strain, well, it's a little more complicated. And strain can manifest itself in terms of the distortion of a shape, or it can also manifest itself in terms of the extension of a shape. And I did just want to kind of emphasize one thing with strain, if I can. There we go. So with strain, I don't think I really made it clear when I did the example, and this is maybe a little bit basic, but I just wanted to make it kind of clear. When you have a bar, is it okay? We've started class. Thank you. All right. So if we have a bar, okay, and there's a load on that bar, and it has some displacement like that, okay, what we said, okay, is that if I'm interested in this is the x direction, right? We said briefly that the strain in the x direction is given by this delta over the length, right? That's a change in length over the entire length, right? So it's the change in length at the end, okay? So, maybe it goes out to here, something like that. So I want to make a point, though, that I didn't make a point in the video or last time very clearly, is that this strain, though, where is this strain present? Okay, I mean, we calculated it based on the overall deflection, okay, divided by the initial length. But where is the strain present? Yes. Exactly. It's present throughout the entire length of the bar. Just like the stress, okay? So, if I come in here with some, little glasses here, right? And then I like look at this nice little element right there, and I bring it down over here, okay? And now this is a small element, right? It doesn't really care what delta was, okay, for the entire structure, but we do definitely care, okay, right, about how much it's being stretched, and it's undergoing that epsilon x there. Okay, now epsilon is of course unitless, right? That's non-dimensional. And so, this is a really small element, so you're going to have to be careful if this is a dx and this is a dy, for example, okay? And so, you could come up with some little, little amount here that we're thinking about. But I just wanted to point out that this strain is in fact present throughout the material, okay, and throughout the whole bar. Okay? Now, in order for us to relate stress and strain to each other, okay, we have to know something about the material. So you're like, well, what are you talking about? You might not have made the connection, right? But we were calculating these stresses with the force, and then we were just saying, oh, here is some delta, okay, and now calculate the strain. And we did do some connecting, right? We kind of connected through the idea that there's a stiffness, right, a K, for the structure. That's not a material property. That's a structural property. Okay, so if you go back, we talked a little bit about this, I think maybe the first time we met, that there are properties of structures. Like, I can give you the stiffness, of this table, and maybe it's, I don't know, 10 kilonewtons per millimeter or something, okay, in this direction when I sit at this location. So at this location, in that direction, okay, and that's a structural property. That's what the table is experiencing or manifesting. And of course, that table, that its structural properties, they're based on the geometry and a bunch of material properties throughout, right? So we've got some material property for the steel. We've got some material property for this tabletop, okay? And we can begin to think, oh, these are bars that are going to be in compression if I'm sitting on it. And we can think, oh, this is a beam, or it's really more of a plate in reality, but it's going to be experiencing more deflection at this midpoint if I sit over here than it is over here, okay? So we have kind of this composite idea, or, well, we shouldn't say composites in that context for mechanics materials, that's something different, but we have this idea of summing up the properties of the material into structural properties. But as we've said before, you can't always put the thing, your product, in a testing machine, right? Like, I don't have the ability to stick the Eiffel Tower in a huge crushing machine to see, if it's going to withstand loads due to wind or other circumstances, okay? So what we instead attempt to do is design work, right? And in order to do design work, we need to know something about the materials that we're selecting. So that's where tensile testing and compressive testing come into play, okay? So what you see here are test specimens, all right, and they have, in this case, they have little threads on the end that you can screw in to the machine head, and you can also have these types of specimens that are more rectangular that you clamp. Okay, when you do the lab, starting next week. All right, so some of you will have the opportunity on Friday, a week from today, to start the lab. And if you haven't signed up, please sign up. Right, we have a little bit of a safety factor, but not much of a safety factor. And so I think a lot of people signed up for the first few weeks, but if you haven't, please sign up. And if you did sign up, we have the ability to track, okay, the edits on the Google spreadsheet. Don't miss it, right? And expect that you're just going to find another spot. Okay, please stick to the spot that you have. Anyway, so when you get into the lab, you're going to see a machine that's capable of clamping on both ends of an aluminum test specimen and on both ends of a paper specimen. Okay? And there's a video there's some information on the website on engineering-content.com at the bottom underneath, like, session 25, okay, for mechanics and materials. There's something about the lab. Okay, so if you want, it'll speed up. Your group will be happy if at least one of you has looked at some of that material before you go in, okay? Or you'll just have to stay a few minutes late, either way. Okay, so what we're doing here is attempting to rip material and then pull it. That would be a tensile test. Or we have these systems where we can compress the material instead, all right? Now, what kind of class of material do you think this is? Any idea? What does that look like? Concrete, yeah, okay? So often the ceramics or the brittle materials get tested in compression. Okay? And the ductile materials, they often get tested in tension. Okay? The brittle materials, they often have more strength in compression than they do in tension. Okay? And they are brittle. In other words, they have kind of this catastrophic behavior. They just shatter, okay, like glass. And the ductile materials, they kind of tend to kind of neck. Okay? And we'll talk more about this in detail when we meet again on Tuesday, but this is just to kind of give a little bit of context. So we've talked about stress, we've talked about strain. Guess what? These machines, they tell us the relationship between them for a given material. So as you stretch the material, you already have this intuition, okay, that means that the strain's going to go up. And you also already have this intuition that the force required to stretch the material more goes up, which means that the stress inside the material is going to go up, right? So there's already this idea, right, that as stress increases, strain is going to increase and vice versa. Okay. And I am now going to take a brief moment for student identification. Okay. And we're going to take attendance a little early today because I know, and I actually would love for many of you to go to the club fair. Okay. This is something that has been planned. Okay. So for everybody to get a better idea of what's going on in the department. So this is when you can. This is like the one time where like I'm completely fine with a mass exodus. So take your attendance. Thank you for showing up. If you want to stay, please stay. I'm going to stay. Okay. But if you want to get a hot dog, I suggest you get out there. All right. If you don't care about a hot dog, then you can wait. All right. Okay. Thank you. All right. Sure. Enjoy. Okay. All right. So, thank you, everybody. So for those of you who have chosen to stay, I hope it'll be worth your time. Okay. So, like we were just saying, we have these relationships between stress and strain that we characterize in our tensile testing machine. Okay? And for the materials that we are concerned about in this class, primarily the metal alloys like steel and aluminum, we don't expect a whole lot of strain. Okay? Steels often will fail at around 0.1% strain, in fact. Okay? The polymers may be 1%, or the thermosets. And then other polymers that are the rubbery ones, they could be 10%. The elastomers, this material EcoFlex that's been used in soft robotics, it fails at 900% according to the sheet. Now, if you do that multiple times, good luck. But that's kind of like a one-shot kind of thing. But 900% is a huge amount of strain, right? That's like taking the gum out of your mouth, essentially. So for our intents and purposes, we are going to pretty much be using a very small amount of strain, and the area is not going to change that much. Now, what's interesting is that you may think, oh well, area should just be conserved, right? Because you got an idea of volume conservation, right? Not necessarily, okay, with these materials, okay? In order for the volume to be conserved, it has to have a very special property where it's we'll get to this in the next lecture, okay? Where it's what's called its Poisson ratio has to be very close to a half, okay? But in this case, we're going to say that the area is more or less the same. And and again, it's the cross-sectional area, right? So if I've got this thing that I'm pulling apart, right, it's the cross-sectional. Also, when we calculate strain, we are going to keep the nominal length constant. Okay, we're going to say that our strain calculation is going to be related to the initial length. And so just to kind of give some context here is the nominal length. That is the delta that you're experiencing, okay? And this length, all right, is measured. You'll see this word gauge, all right? And sometimes I use gauge, and sometimes I spell it differently, okay? Instead of G-A-G-E, I spell it G-A-U-G-E, all right? But this is kind of the nominal length that's of interest to us, and we might mark it. Why do you think we pick a gauge length that is less than the overall length? What are your thoughts? Okay, Mark?
Is that where it'll break?
Huh? Yeah, it's going to break, right? Do you expect, if I'm pulling the material apart, do you expect it to break in the grip section that's big and fat and wider? No, you hope not, right? You hope that you can get it to break in this test area, okay? And that's what we do. So it's also a detail sometimes is that you want this transition to be somewhat smooth, okay? Because sharp edges don't typically affect things too much in static loading, but definitely fatigue, they affect things. And sharp edges, if you have like an elastomeric, a rubbery material, those sharp edges can definitely they can become places where cracks will propagate, okay? So you typically see like a nice smooth transition, and then you hope that your system is going to break in the middle, somewhere, okay? And what you would do, sometimes there are like these little probes that you put right on the material itself. You attach them, and then they are very sensitive, and they'll be able to measure the very, very minute changes. We're talking hundreds, if not less, microns. They'll be able to measure this, okay? And sometimes people put dots. They paint dots on it, and they use what's called digital image correlation, and they have a camera that's able to calculate the very precise small motion as well in your test region. Okay? And the machines that yes, question.
Is there ever an example of strain in a non-tensile sense, meaning in like compression?
Oh yeah. So absolutely. So if you do a compression test instead, right, then the strain just becomes negative. Okay? And then we and I even said in one of the videos for one of the homeworks, like I just said that the change in length is 0.8 or whatever it was millimeters, and that's not really super specific because you want to give it a direction as well. So yeah, strain can definitely be negative, and you can keep that in mind. For these right now we're talking about tensile tests primarily, so it's going to be positive. And so this type of strain where you look at the delta over the original length is what's called engineering strain. Okay? And this type of stress is called engineering stress. And again, for these types of materials, they're pretty exact. True stress, okay, for example, would take an account the amount of necking you will have. So as you, like if you stretch a rubber band, and if I were a better professor, I would have a rubber band here and I'd be stretching in front of you, but we'll use your imaginations. You got an idea that that cross-section does decrease. Okay, and actually rubbery materials, because their Poisson ratio is pretty close to 0.5, or maybe not because we have some parameter, but just because of the way they are, volume is often conserved. Not so much with the metals, okay, but in those materials it is. Okay, so again, I'll just say, if you see the word gauge on an exam, please do not freak out, okay? It just means, you could just ignore it almost, okay? But it just means that it's the initial length, or it's the length that we're monitoring, okay? In our test setup and how it's changing. So there is quite a bit of variation in these types of tests, all right? And hopefully, you know, we're not going to do major statistics here, or pretty much any statistics, to be honest. But you can appreciate that one sample is not going to break at the same force, same stress, or same strain as another sample of that same material. Okay? And so what we do is, we'll talk about this later in the class, we prescribe safety factors. Okay? So, you know, if I test a material one time and it breaks at 100 newtons, all right, I'm not going to go design a skateboard that then has, that induces, I know it's going to induce exactly 100 newtons, or under 100 newtons of load, it's going to induce a bending stress that's going to be equal to the stress I calculated, right? That would be kind of silly, okay? So what we do instead is we say, hey, you know, we think, like the engineers in the back room are like, hey, we think that really it will only support 100 newtons in tension, for example, okay? But with the, you know, with the jumping and the impact that we expect, with the, you know, variability in the weight of the users, we're going to give it a safety factor of 3. Okay, that's pretty high, but that's not uncommon. Safety factors have come down as our ability to estimate conditions and run simulations have improved. But for your furniture and various things, right, you know, you can have pretty significant safety factors. So really, you know, you should only apply 33 newtons if I do a safety factor of 3, right? Even though I know in my material testing it's going to break if it's 100 newtons, I'm going to make sure that that I, you know, that we add some extra safety in there. Okay. So anyway, but there's variation in these in these samples because of how the material might be mixed together or alloyed together because of microscopic imperfections, temperature, a bunch of different factors. Okay. Now, what does the result look like? Well, so I should ask. Well, I don't have to ask. Who has done tensile testing? Anyone done tensile testing here? Okay, yeah. What were you testing?
Basically the strength of the material before, like it's building strength before it snap.
Okay, great. What kind of material? Are you allowed to say, or is it like classified?
No, rubber band.
Rubber band. Okay, good. You did tensile testing. Okay. Yes. Oh yeah, that's right. That's me. All right. Yeah. Okay. Yeah. All right. Okay. Some of you saw me screaming, right, and cheering. Okay. Good. You have done. I forgot. That's right. That's I was there. Okay. I've been with you. All right. Okay. Yes.
Back in high school, I took a class where someone built like structures out of like some sort of wood.
Yeah.
And then we would try to like test the strength of it.
Yeah. So good. So with wood and stuff. So, you know, if you don't have a really expensive machine, you can get some pretty good ideas by just using dead weights. Okay, you know, make the cross section small enough and then hang weights. And so there was this time where I was working for a professor who was making a lot of money, and I was making just a little bit of money. That's how it goes, right? But I was a grad student, and it was good money for a grad. It was really good. Actually, I don't get paid that much per hour now. But anyway, so there was this case where someone had gotten hurt with a bungee cord. Okay, and so what we did, it's not exactly this, but apparently the bungee cord had been wrapped over kind of a metal plate, okay, with an edge. And so I got a metal plate, and I got some bungee cords, and we put them over the metal plate, and then I just put dead weights on there to see, okay, at what force would this thing break? Okay, and I was like, I just don't want to get hit in the face with the bungee cord, because then they will have another case against them, the bungee cord people. So anyway, so that yeah, you can do these types of experiments, like you're saying, with wood or various things in your basement. Okay, okay. So this is what the curve looks like. Do you see that on the y-axis we typically do stress, and on the x-axis we typically draw strain? Okay, and this is called a stress-strain curve. And in general, if this is just for your good to know file as experimentalists and as people who read things, if someone says velocity versus time, right, versus time versus velocity, typically the first parameter is the y-axis, okay? And the second parameter in the versus is the x-axis. It may be trivial to some of you, but it's nonetheless good to know that this is a stress-strain curve. Yesterday, my daughter, coincidentally, was like, hey, she's in 5th grade. She's like, there was this diagnostic, they do these, not diagnostic, it was like a pre-test or something, and she's like, they were asking me to identify the dependent and the independent variables. I'm like, oh, really, in 5th grade? She's like, okay, all right. And it's just like, I don't think they taught him this, but she's like, so, they were giving me the weight of the fruit, and they were giving me the price, weight per dollar, and then they were saying, here's the cost. And I had to figure out which one was the dependent variable or dependent variables, and which were the potentially independent variables, okay, or variables, right? So we're like, oh, well, what do you think? You're like, you can't really change the weight of the fruit. And the price is kind of, in this example, kind of fixed, right? So these are going to be what we consider to be the independent variables, right? And the dependent variable is going to be the total cost, because you're choosing, okay, what the factor, multiplying those two factors against each other. Anyway, so I thought that was fun. Even in 5th grade, they're teaching these concepts now, right? So what's interesting here is it's the same thing here. We typically are applying strain to the systems, and we're looking at the stress. That's just typically how these things are set up, okay? And so when you go to the lab, you're going to be applying strain. You're going to have a crank, and you're literally going to turn the crank, and that's going to provide the displacement, okay? And then we're going to have a load cell that measures the force as we apply that displacement, okay? And we are going to get to this kind of interesting regime, or this point, okay? So we've been using spring constants to describe these materials, right? Spring constants are associated with a linear behavior. Voila, there's a linear behavior to a certain point, okay? So technically, we call that the proportional limit. And then there's something, and so another interesting behavior, so you can figure out what the slope of this is, and we'll talk about that in a minute. That's something called the Young's modulus. But let's for now just say, look, if you go only up to the proportional limit, you can release it, and it goes back to its original shape. Okay? If you go up to the elastic limit, okay, and then you go beyond that a little bit to the yield stress, or the strength, yield strength, okay, you may not get exactly to where you started. Okay, and to be honest, we're not. When you take if you do properties, okay, the mech prop, right? They'll go into more of the details of what's going on here, but for our intents and purposes, these three parameters, I mean, maybe I've put it on an exam once where I said something like, okay, this is the proportional limit, or this is the elastic. But what you'll see most often when you go and look at a spec sheet is you'll just see yield strength. Okay? So up to the yield strength, approximately, this material is behaving in a linear fashion, okay? And it is going to return. If you stay below that yield strength, it'll return to its original shape. Okay? But once you go past the yield strength, interesting things begin to happen. Okay? And mechanicians don't really, well, okay, some mechanicians, plasticity is their thing, all right? But for our class, no, plasticity is not our thing, okay? We want a design to stay in here. But materials, we need to understand, they will go on for different amounts of strain in this plastic region. And once you go plastic, you're not going to return to where you did originally. Okay? We'll talk about that a little bit. Maybe I should, well, I don't know if I should digress on that now. No, I will not digress on that now because I had to explain a couple other things. Elastic modulus, for example, first. Okay, so up here, this is the ultimate strength. Do not design your product unless, I don't know, you just like it's a one-shot type of thing for its ultimate strength, or if you're actually doing fatigue calculations. So for fatigue calculations in DMC, Design Mechanical Components 342, you'll get a better understanding of what it means for a material to experience cyclic loading, but we won't cover that here. Okay? And there's a fracture stress. Okay, so that's kind of what the stress is when it finally fails. Okay? And here are examples of what a stress strain curve looks like for a brittle material and what it looks for a ductile material. And again, you kind of got this idea already that a brittle material, it doesn't really play around in the plastic regime. It's done, right? It shatters its glass, bang, right? That's where this X is that I drew in afterwards. And that's also kind of something that maybe is obvious but not obvious. Typically, once the curve ends, you've really hit failure. Like, we usually think of yielding as failure in this class, but if you get to this point, you no longer have connection. And then a ductile material is going to go on for a little while and then break. And you see that the slope is much, much less here. And we'll talk about some models for this the next time that we meet for being able to do simple approximations for these types of behaviors. Any questions up to this point? Any more questions, I should say? Yes?
So why is it that just before the fracture, the strain goes down a bit?
Yeah, that can be, I will hand wave there and say, okay, there's some grain boundaries, there's slipping, some sliding at the molecular level, and yeah, things then become kind of, once they've kind of locked into place, then you get what you consider to be, so you create these dislocations in some materials, okay, the metal alloys, and then things kind of lock again into this next level. And even though it's getting flatter here, all right, and we'll talk a little bit about this, you actually enter a region that's called strain hardening. So now these dislocations, they're kind of moving and sliding against each other, and they actually end up making the material harder and stronger. Okay, I'll explain this in a second. All right, not just in terms of the graphs, not in terms of the physics behind it. Yes.
Is there any equation to demonstrate like where it says area under curve is equal to absorbed energy, or do we worry about that in this class?
You definitely worry about it, and we'll worry about it more on Tuesday. Okay? But yes, why would you care about that? Since you asked the question, why would you care about this area under the curve?
I mean, someone might think like how much energy would be required before it breaks.
That's right. That's right. That's absolutely right. Maybe you're designing a bumper. Okay?
Yeah.
We're close to New York, right? So I've gotten better. All right. I no longer. So I lived in Massachusetts for a while, and I had an old car. I still have an old car, but I had an even older car, And I was like, yeah, you know, the Boston bump, okay? But I now don't hit other cars, okay? Not on purpose, at least, okay? Yeah, like I have my kids go out, and I've done some good parallel park. I'm not the best, but I'm like, there are a few, like, I'm like, that's worth the picture, you know? Because it's like this much on one side, this, and like, you know, we're at the shore, it's like, yeah, what's up? We got a good spot. All right, so anyway. Yeah, so bump, like a bumper, for example, something that you want to absorb shock, right? You would care a lot about these types of properties. Okay. Now, we already said it's often it's difficult to distinguish between these three, and so we don't in this class. Okay. And we also talked about elastic behavior, and so if we're in this, along this line, it goes back, okay, which is a spring, like a spring does. And if you're in this region, it's plastic, and it doesn't go back all the way. You actually have permanent strain, okay, or residual strain is what we call it as well. If you unload, once you unload, okay. And let's talk about the elastic region a little bit. Okay, this elastic region has a slope, and we're going to introduce this parameter called the Young's modulus. And this Young's modulus slope, it's rise over run. Okay, you're like, oh yeah, okay, I understand that. Yeah, that's simple. What are the units then for this system of its elastic modulus? I think Mark knows, but someone else? Okay, back there, yes. No, but we're thinking along those lines. Anyone else? Back in the back. In the back. Okay, you guys are good. You guys are good. Give it a shot. What are the units? You only got a couple choices. Who said that? Okay, why pascals? Stress over strain. Exactly, right? That's the rise over the run. And what are the units of stress? Pascals. What are the units of strain? Dimensionless. Okay? So the elastic modulus ends up having the same units as strength, okay? And it has units of stress, of course. But typically, the values for Young's modulus are much higher, and they're in the gigapascal range, okay? Because what? The stress is really small. Remember we were saying 0.1% is what you have for these metals? So you'll find that the stresses that we calculate are maybe on the orders of tens of megapascals. Okay? And a lot of times the yield strength, like once you get to where it starts to yield, and we'll have slides on this, those are going to be hundreds of megapascals. And then the elastic moduli are tens of gigapascals. Okay, so giga is 10 to the 9. Meg is 10 to the 6. Okay, so if I take the slope here, okay, the rise over the run, then I'll be able to get it. Now, I mean, this again, so a couple of years ago, our chair of our department was like, students are graduating without knowing how to calculate the elastic modulus of a material. All right, I was like, oh, okay, well then I better do something about that. All right. So if you run into the chair of our department, you better be able to, no, just kidding. But you in this class, you do need to know how to calculate elastic modulus, all right? And it's just rise over run. So you tell me, how do you do, if you were given this chart, what are your options for calculating the elastic modulus? No equations besides rise over run. What are your options? How would you do it? Yes? Yeah?
Just calculate it that way.
Yeah, okay. And what would be some candidates for your 2 points? So I need something, comma something, and I need something, comma something, right? So what would be your candidates? Yes?
2 points at the origin and 1 point at the yield strain.
Yeah, that's a very good spot, right? Say, hey, I'm going to go with the yield strength, right? And I need to know, but then I got to calculate what the strain is there, right? And then I'm gonna say, okay, minus, right? So rise, right? I'll do the rise and this one, the origin, okay? And I'll do the strain here and the origin. Well, that's the origin is 0, 0, right? So it's just often, not always, all right? It's often just the yield strength divided by the strain at the yield strength, okay? And that's all you have to do. So if the yield strength is 100 megapascals, and the strain, the yield strain, which is not a term that you'll hear me use very often, but the yield strain is 0.1%, right? 0.1% is 1 over 1,000. So 1,000, right? So I had 100 megapascals over now 1 over 1,000. That's 1,000 times 100 megapascals. Boom, megapascal, gigapascal, right? That's it. So now I have 100 gigapascals as my elastic modulus. That's all you got to do. All right, and so you can do it. Yes?
What's the difference between the elastic modulus and Young modulus?
They are the same.
Okay.
Some people like to say elastic modulus. Some people like to say Young. It's
Also,
okay.
Is this the same Young that came up with the double slit experiment? Like,
Maybe. You're beyond me, to be honest. All right, you outsmarted me on that one. Okay, yes.
Well, is it possible to have, like, because it's possible for like a graph to have like 0 strain, but then you still have some stress, or would that ever be possible?
Okay, good question. So let's put it this way: if you had, what would the elastic modulus have to be for that to happen? To have stress but very little strain. What would the elastic modulus have to be? Or what would it be like? Would it be a low elastic modulus? Would it be a high elastic modulus? Would it be an infinite elastic modulus? Yeah, right? So the higher the elastic modulus, right, that's the slope again, right? If you wanted to have 0 whatever strain and you're putting in force on something, right, essentially your elastic modulus would have to be infinite. Okay? And so now you've got an idea, right? If we go back to our beautiful table, and I won't talk to the table or the chair. Apparently, some people do that. But if you if I go back to this example, right, then I've got an idea that okay, the elastic modulus of the metal is going to be a lot. I just know because metal. This is steel. Anyone know the elastic modulus for steel? Yeah.
210 megapascals.
Oh, you were so close. 210 gigapascals. All right, good. All right. Yes.
Is it possible to keep like a material like a constant state of stress for like to keep it like enhanced properties?
I don't. Explain that a little bit. Or I don't know if I understand. What do you mean by enhanced
So,
properties?
Like, the strain level, right? And like at a certain like strain, is it possible to like keep it at that state for like a while to make enhanced properties? Like you mentioned.
Okay, so we'll get into this. If you're in the plastic, all right, region, then yes, it does enhance its strength. Okay, and one of the interesting things about structures and steel, okay, and you'll learn this in this class. Often the highest stresses, like for a bar, right, we're like, hey, everything's uniform in the bar. But for shafts that twist and for beams that bend, the highest stresses are actually at the surface. Okay? So sometimes the goal is just to enhance the strength of the material or the structure at its surface. And steel cooperates synergistically with this effort. Okay? So what happens is that you can quench a steel with temperature. So you heat it up, you let it stay for a while at a high temperature, and then you put it in water, quench it real quickly, and then it becomes very hard. And because there's a thermal gradient as that quenching is occurring, the hardest, strongest portions are going to be at the outer edge that got cooled the quickest. The other thing is shot peening. So people will purposely shoot little balls at the outer surface of structures to like ding it, okay? And by doing that, they've introduced plasticity to just the outer surface, which makes it stronger, quite frankly, and more resistance to potential failure. So holding it at a value less than, say, yield, probably not. Even holding it at a stress level that's in the plastic regime, I have trouble thinking of how that would help. But if you do it like once and then you release, which we'll talk about, that does help. Okay. All right. Okay, so Hooke starts to kind of come up with these relationships between stress and strain. You know Hooke's law. And then Young, he's kind of one of the people who's been responsible for relating stress and strain. But look, it was like, that's a lot of years between coming up with the relationship between force and displacement and stress and strain, although they're very related to each other. Okay? And we're probably forgetting a bunch of people in between. This is the formula. Where is this formula relevant? In the elastic regime. Okay? So this is your biggie. Now, this is for a special case. We'll get in, this is for the elastic regime up to the proportional limit, which we consider to be the yield strength for this class. And it's also assuming that we have this uniaxial loading. Okay? We'll get into situations, and so when we say uniaxial loading, this is the relationship between the stress and the strain in the same direction. Okay? We'll talk about stuff that's not in the same direction, and it's not this simple for the equation. But sigma equals E epsilon is your friend. Okay? Another story, had a friend, I still have this friend, nice person, but he was interviewing for a job, and the guy that came out right before him was like, I couldn't remember the difference between stress and strain. It's like, ooh, sad, right? I mean, granted, these are seniors, and this is sophomore year, okay? But you're going to see stress and strain a lot, okay? In this class, in DMC, in aerospace materials if you're an aerospace engineer, in aerospace structures if you're an aerospace engineer, senior design, you're going to see it should come up a bunch. Okay, so I already kind of talked about how you could quickly calculate the elastic modulus, all right, but first you got to specify the cross-sectional area and length for a material. You're going to put it in a machine, and then you have a certain strain rate. Okay, so you're gonna specify that constant rate, and in the lab you're gonna turn the crank, and you're gonna turn it about that speed that I'm turning right now. Don't go like this, and don't go like this. You'll be there forever. Okay, but we turn it nice and easy, and you specify that rate. You got to measure the strain. Okay, you got to measure the force, and the other thing in these tensile testing machines is there is compliance. The machine itself has compliance. Okay? So we're doing kind of a cheap, well, yes, maybe that's not the right word. We're being very economical in our testing. Okay? So the machine doesn't have a separate strain gauge or device, extensometer, for measuring the displacement of the gauge length. Okay? It's actually just using the motion of the head. Okay? So like there's a head that's going to be moving, and then there's a base. Okay? So knowing that it has some gear ratios, and probably has an optical encoder somewhere in there. I haven't actually, I don't know exactly how they're doing it. But we're just using the displacement of the head relative to the bottom, and that seems to give us good enough results. And then there's a load cell. So the load cell is sitting on the bottom in our case, and the load cell also has some compliance in it because, well, it's pretty hard to magically measure force without having some type of displacement associated with it. Okay, so that, but of course that stiffness has got to be pretty high and not affecting our system. So they're going to be measuring the force, and we'll say force versus the delta. Okay, and you're going to convert to stress and strain just like that. So I mean, I like delta better than, these are my own slides, so I should probably change them. But anyway, at least from this Wikimedia Commons thing, they say that was lowercase l. Okay, so I don't know. Yeah, that's fine. Okay, and we already said it's the rise in stress over the run in strain. Okay, any questions, any further questions? I like the discussion. Okay. Yes, Michael.
Will you be measuring like if, the cross-sectional area, like H shrinks, like if it's stretched apart?
Good point, yes. So that'll be something that you do, yes. So I think the thickness, well, it depends. You're going to do paper samples and you're going to do aluminum samples. The nominal length or the nominal width is about, I think, 6 or 10, I can't remember, millimeters. And then the thickness is, for the paper, the thickness is only like 100 microns. The thickness of the aluminum is something like a millimeter or something like that, millimeter or 2 millimeters. Okay. But there are calipers in there. You'll be able to measure the thickness. Yes, you have to know that cross-sectional area. Okay. Again, someone hands you a test sample. They tell you it's a length of 10 centimeters and a diameter of 1 centimeter. So in this case, it's cylindrical. Okay, and then they tell you that in the elastic regime, you have 10 kilonewtons, and you measure an extension of 60 microns. So we can calculate our force over area for our stress. We can calculate our epsilon, which is delta, or little l over L, depending on how you do it. And then we can calculate out the elastic modulus, which is, right, we said that sigma equals E, right? So sigma equals E epsilon, and we have E is equal to sigma over epsilon then. You already kind of got a taste of this actually for that member in the truss, okay? Of, the force over pi d squared over 4. Okay? I probably, until the day I die, will probably mess up this factor of 2. Please, I'll try not to, okay, I commit. I will try not to trick you, okay? But if I do, I told you, all right? You will be given diameters or radii for different objects, okay? Please, if it's diameter, it's 2 times the radius. I get this confused all the time, okay? And if we do it, I guarantee someone's going to be off by a factor of 4 because of this, all right? So anyway, and we can go ahead and we can calculate out the, so here we go, converting, and then converting here as well, and getting the, in this case, this is the delta, all right, converting, and then getting over to gigapascals, and voila, okay, that's the result. And as someone pointed out, who was it, you, who said the elastic modulus of steel? It was you? What's your name? Andrew. Okay, so as Andrew pointed out, all right, elastic modulus of steel is typically around 210 gigapascals or 200 gigapascals. So there's a good chance that this material is about that, is steel. Okay, and here's some code. All right, so the Python. Yeah, in the videos, look, I'm trying to do a lot of the Python. I know it's trivial or not. If you got what you got, don't watch the rest of the video, okay? But every now and then, it's useful to keep watching and learn about the Python as well. In fact, I think it was useful a couple of times in the last assignment because we were talking about a little bit about that solving the matrix for the truss. Okay, so there are a lot of different materials here. You don't have to memorize them. The only one, so we've made deals, all right? So near the end of the semester on the final, if you like, I'll give you a freebie for the first question on the final. And it can be something like, what is the elastic modulus of steel? All right. And everyone gets that one right, I hope. So when we get closer, we can make that public service announcement. Okay, steel 200, okay? And I guess I guess I had the conversion, but it's about, I don't have it here, but I think, 6.89 megapascals is 1 KSI, 1,000 pounds per inch, okay? Squared, 1,000 pounds per inch squared. Okay, so This is, these are units, these are actually megapounds, okay? Megapounds per square inch, all right? So that's an interesting unit, all right? And these are gigapascals here. So this is just showing them. So steel, 200, in that ballpark. Or 30 mega PSI, okay? Or 30,000, more common would be 30,000 KSI, but sure, you can do this mega thing if you want. Aluminum, typically around 70 gigapascals. That's a good one. I don't really remember titanium off the top of my head, okay, but sure, it's around 117, 116, and then wood, all right, and polystyrene, right? Okay. So why in the world do we use all these different materials with all these different elastic moduli? Why don't we just use one for everything? Any ideas? Yeah?
I would say cost.
Cost, yeah, cost, application, right? So before the Industrial Revolution, what were your materials for general construction? Huh? Stone and wood, right? Those, you kind of had those two options. That was about it. Yeah, they had some ideas of making different types of paste of things, right? But yeah, and we did quite well. And what were the initial planes made out of? Wood, right? And balsa wood is still a really amazing material. Why? Because its strength to mass ratio or strength to density ratio is amazing. Okay? And so it's really lightweight. Okay, so wood is not to be underestimated as a material. And we're glad that it happens naturally, yes.
So, in general, is it correct to say that the higher the elastic modulus, the stronger the material? Or is that more of a...
Yeah, so let's good. All right. So it depends. All right, it depends. But yeah, that's not a bad kind of thing to put in your mind. All right, not bad. But the steels are amazing. Again, going back to steel, because the steels can have a very tunable strength. But you know what stays constant? Elastic modulus. So you'll find all kinds of different alloys. You know, they put all kinds of different stuff in them. You know, they might have whatever, some nickel, some whatever, like chromium. They put in these little alloys, and carbon, of course. Okay, you have different levels of carbon. But the elastic modulus stays the same. But you can have, really go from like 100 megapascals to like 1,000 megapascals for strength in a steel, just by its processing and by its alloying. Okay, so you'll see what's nice about this chart is it's pretty clean. You see one elastic modulus per one material, except for the polymers. The polymers are different, but at least for the metals, they stick to their elastic modulus. Okay. Ceramics have a pretty high elastic modulus, and they also have very high strength, but they're very brittle. Okay, and ductile. Yes, Michael.
I was just curious. I know this is about things like materials tendency to stretch. Included in this is there the ability to stretch before any permanent deformations?
Okay. Yeah. So we'll talk about permanent deformation in a few minutes. Okay. Yes. Okay. All right. So here are the ones to remember. Although I don't really remember titanium. Okay. But these two I definitely remember, and it's good to know that there's quite a bit of difference between wood and the thermoplastics. Okay. And the rubbery ones are even less. Okay. So now, do you remember in the first class? We talked about these scaling relationships. And we talked about spring constants in materials as well. And we were just saying, hey, here's a 2,700 pound roadster, okay? And how much is the bar going to extend? And I had to give you this K is 165 kilonewtons per millimeter. Okay? But now, you all know something very powerful. You know that if I tell you what material something is made of, you can go to a chart and you can figure out what its elastic modulus is, and you can calculate out what the effective spring constant would be, right, of this material. So we could that would be maybe going backwards, right? But let's just look at some things here. So strain, you can calculate. Stress, we can calculate. That's the force over the area, just like strain was the delta over the length. Okay. And now we can calculate the elastic modulus of the bar. Okay. And that elastic modulus, right, that's going to be, because I have some data point, I have a strain and a stress, and I'm assuming that I started at 0, 0 with no stress, I have no strain, so I can just divide the stress that I have here by the strain that I have here, and I get 210 gigapascals. Right? So I handed you a problem, and I had to calculate out the K, essentially, in order to know, because I said, hey, that's going to be steel. I'm going to make this bar out of steel. Okay? And so now we're starting to see that there are ways that we can go from the material that we're selecting to its elastic modulus on a chart or a spec sheet to figuring out what kind of, if we go backwards, what kind of strain and stress we expect. Okay? And then in a couple lectures, we'll, I guess, formally introduce how to go to the K. I guess I skipped. There's an equation. It's called PLE. All right, but there's an equation that we'll use for that. Okay. Hooke's law. All right, so here we go. We're going to go through PLE. Actually, not in a couple lectures, right now, sorry. Okay, this is it. You see this? So we have Hooke's law, sigma equals E epsilon, and F equals K delta. And we have sigma equals F over A, and we have epsilon equals delta over L. So now, we redo some rearranging, so we have F over A equals sigma, or this is sigma, right? And that's going to be equal to E epsilon, so I put in the E, which is just an elastic modulus, which I don't know. And then I have a delta over L, okay, that's a strain, and I can rearrange these things as you see here. Okay. And if I go back to my general idea of what is F equals K delta, I now know that the elastic modulus is equal to KL over A. So we rearrange things, and this is the common formula. So K equals EA over L. Sorry for getting a little lost. Okay, so what does this mean? It means that the stiffness of a structure is dependent on material properties, for one, and for two, it's dependent on geometry. Material property, elastic modulus. Geometry, cross-sectional area, and length. This is for a bar. Okay? So if we increase the elastic modulus of a material, the stiffness is going to increase. If I increase the cross-sectional area, the stiffness is going to increase. If I increase the length, it decreases the stiffness of it, right? And that's something you can go around now, and you can think of the world as a bunch of bars. Okay? Not that you walk into, but bars that you might step on, okay? And you can be like, oh, hey, you know what? That's a little squishy there. I can think of some type of bar that has a lower elastic modulus. Okay? You can go down the hall. Someone was pointing out to me the eyesore that is like this wooden plank that, or like, it's like the piece, there's like a piece of plywood that you just walk over every day, right? So you could go over there and kind of jump on it and be like, hey, that's kind of squishy, versus the hard, floor that's right next to it. Don't jump on it and break it, okay? But anyway, okay. Now, this is the PLE formula, okay? Delta is equal to FL over EA, or FLE or PLE, because often we use P instead of F, okay? So for a bar, we have an idea now that if I'm interested in displacement that it has, then I'll have my force, I have my length, and I have my E and my A, and I can calculate the displacement. Yes?
If we have a bar of variable area, the cross-sectional area, would that always just go to the weakest point or the thinnest point, or would it be like some other stuff?
Excellent. Okay, so right now we're talking about effective stiffness. Okay? So let's say I have a bar, and then I have a big bar, and I put them together. I magically weld them together. And now I ask for the elastic modulus, or I ask for the stiffness of the entire bar, the bar, small bar plus big bar. How do you solve for that? Okay. I'm applying force on the ends, and I'm looking at the overall displacement. How do I solve for the effective stiffness? Yes?
That's 1 over K effective equals 1 over
That's
K.
exactly right. So now right, so you can break it down into, okay, here's the effective K for this region with a small diameter. And here's the effective K for this region with a large diameter. All right? And once I have those two Ks, it's like springs in series. So you can make some pretty good approximations. Now, to your point, yeah, if you've got a force on like a small bar and a big bar, and they're in series with each other, absolutely, the stress is going to be higher in the smaller cross-section than it is in the larger cross-section. So, yeah, you're going to have an issue with the smaller cross-section breaking before the larger cross-section. Because in series, the force is the same, but the stress doesn't have to be the same as the cross-section changes. Good. Okay, so there'll be some assignments and calculate the elastic modulus, okay, for the material shown in this graph. Okay, this is another problem that you have that we get to talk about. Okay, and what I'm assuming here is that the weight of this acrylic sheet is distributed evenly between these two cables. So that means that the force is half of mg, right? Mass times gravity. How do I figure out the mass? Density times length times width times height, right? Density times volume, that will give me the mass. So that's what this problem is expecting us to do. Okay. The indeterminate problem. We might have glossed over it, but we didn't completely. Skip the fact that so remember this is the two section bar in between two walls. I apply a force, okay? And remember, now if I'm interested in the displacement at the middle, and I'm not necessarily interested in that, but if I am interested in the displacement in the middle, and I have that force, right, these two bars, they actually work in parallel with each other, remember, recall? We also talked about how we could calculate the force and say this member or the force in this member. And if you go back to those notes, you'll see something kind of interesting. The force in this member, or the reaction force from the right side of the wall acting on the right side, okay, so right, this force and the internal force in this member are going to be the same. It's the ratio of the elastic modulus, or not elastic, the stiffness of this one over the K1 plus K2. And over here, it's going to be the K1 over K1 plus K2. Okay? So I have the ability to calculate out these forces with this indeterminate problem. Okay? What if I want to calculate the stress and strain in these sections? Okay. Well, yes, we cannot do that unless I know what the cross sections are, right? I can't calculate that out. So, once we know the cross sectional information, okay, and let's say that the diameter is given, and we have them with the same cross section, okay, and we have the elastic modulus, the same cross sectional area, okay, and we have an elastic modulus. So if I want You tell me. If I want stress, what do I do? Let's say I want stress in the right region. What do I do? What's the axial stress in the right side of this thing? Just in terms of variables. Yeah, someone said it. I heard force divided by area, right? Yeah, so it's going to be the F2 divided by, right, because that's what we have in here. Not the F, but F2, right? That's what we have. So that force divided by the area. And then if I want the strain, remember we talked at the beginning how the strain is actually the same across the length of the bar? Well, the stress is also the same across this bar. So then if I want the stress, if I want the strain, what do I do? Yeah, exactly. You have to have a material property here. Okay? You have to have a material property of the elastic modulus. That's why you use sigma equals E epsilon. Okay, good. What's your name? Jelani? Okay. Jelani? Okay, got it. Jelani. All right. That's so. Like, I spent a lot of time in Ecuador, and my last name is, you know what it is Mazeo, right? Well, maybe some of you know. Well, now you know, right? Well, anyway, in Spanish it's Maceo. All right. And people are like, what is that? And I said, no, it's just remember mas feo. Okay? I'm mas feo. Okay, and anyone that knows Spanish, it's worse than salami. And mas feo means the most ugly. All right? So anyway, so thank you for that mnemonic. Okay? And I'm okay with being the ugliest department person here. Okay? That's fine. But I don't think I am. Anyway, so stress is we have sigma 1 is equal to 4f1 over pi d squared, and we have sigma 2 is equal to 4f2 over pi d squared. Okay. And then if we want to calculate out the spring constants, okay, we can do this, or we can relate. If we know, well, okay. So these are true statements, okay. All right, and then we can go about, but we had to use. This is a complicated way. I don't like how I'm doing this, to be honest. Okay, this is fine. That's great. Okay, that's not very useful information. Okay, but we can use it if we want to figure out the lengths, I guess, associated with that. All right, but this is really the equation that I'm glad that Jalami gave us. All right, that we're really interested in the epsilons and how they are related to the stress that we calculate. Okay. All right. Oh yeah, and that's another thing. I have to be careful here. Okay, so in this case, right, the strain that this material is experiencing is and the stress, they're negative, okay, because it's in compression. So it's sigma 2 is going to be minus, okay, the force F2 over the area, okay, so that's a negative stress, and since it's already negative, all right, I don't have to do a negative of it again. All right, but if I were using numbers, I know that my strain is also going to be negative, okay, because it's in compression. Okay. How much time do we have? 4 minutes. Okay. So I do want to cover this though, and maybe we'll come back to it. The conversation at the beginning of the class, or near the beginning of the class, people are like, "Well, what happens if you go up into the plastic region?" And next time we meet, we're going to do some approximations that look more like this. Okay, so this is stress, this is strain. Okay. And a more realistic model might look something like that. Okay, so we'll introduce these two models. You see how this kind of looks like, you know, that plastic region, right? That was going up like this, right? It's kind of coming up, at least until the ultimate, okay? You also know that if I go up this curve, I can go back down and I go right back to 0. As long as I am less than the yield strength of the material, right? So this is maybe not very clear, but let's say that's yield strength, and let's say that this is a yield strain, right? So as long as I stay in that box, everything's happy. But once I leave the comfort of the elastic regime, I've introduced dislocations, again hand waving, and the material can't go back to its original shape. So let's say I get out to here, and I'm still applying the force, or I'm still applying the displacement that gives me this nice equilibrium for the stress and the strain. But then I let go. What happens? Well, what happens is the material remembers its elastic modulus. It doesn't seem to forget that, okay? And it goes down, 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 down. And this has the same slope. I know it's a little bit bad to write E and 1 because you're like, we're never going out 1, all right? But just so you get an idea, okay? We're never going out, but that's the slope. And it will return not to its original state, but it will return to a state that has a residual strain like that. Okay. And what's even cooler in the last minute is this bar is now stronger, because the next time I apply a load, guess what? I go right up here before I start to yield. I don't yield until I get to this line, that plastic line. Okay, so I've introduced some residual strain, but now my new elastic, or my new strength is actually higher than my original yield strength. Okay, everything has limits, right? If you go beyond too much, right? But yeah, it's a really cool property of steels. Yes.
So does the same thing happen when the break happens? Like it breaks, it's gonna also come back down in that curve?
So this is, yeah, it will. If you don't break it, it's going to come back down, and there's going to be a bunch of residual strain. Yeah. Okay. That's true. So you can come out to this point, you can go, but if once you break, you're broken, right? Like once you fracture, that's it. Yeah. Okay. Yes.
Does strength only happen in like the region where the necking occurs, or throughout the whole?
Yeah, so that's a good question. Where the plastic, so you can have different amounts of local plastic strain. Right? So it'd be variable, right? So where you have the most plastic deformation is going to have the most strain hardness. Okay, great. If anyone didn't get the attendance, you don't have to do it again. I'm just saying if you didn't get the attendance, I'll show it, okay? But I think most of you got it when we did it before. All right, see you on Tuesday. There's an assignment due as well. Thank you.